Alright, welcome back everybody. We proved now that every Hilbert space has an orthonormal basis, and then we exploited that fact in the proof of the Fourier expansion theorem. Now in the last part of this section things will become more, I would say, constructive and explicit, because we're playing around with separable Hilbert spaces. Those are Hilbert spaces with countable dense subsets. So whereas early on we had to rely on some pretty abstract reasoning like Zorn's lemma, here in the separable case things work essentially via mathematical induction. Okay, so to make this more precise, here in the first result, in a separable Hilbert space there exist countable independent spanning sets. So this was already written on the slide last time at the end of the video. And those independent spanning sets, they really, model the behavior of a basis that you know from linear algebra and finite dimensional spaces, and they model it sort of much more concretely than our previous notion, which was orthonormal sets not properly contained in any other orthonormal sets. To be more precise here, so these spanning sets, they're really, well, independent. So if you sum up your vectors yj to 0, then this can only happen if all the scalar coefficients alpha j are equal to 0. Well, here though, the difference still to linear algebra is that this capital N could be infinity. But still, you're in a countable situation, so that's not so bad. And then the second property, the spanning property up here, so the set of all linear combinations of the yj's, well, it's dense in H. That is also a small difference to linear algebra. There you don't have to worry about density at all. Okay, so let's prove this little result. It's essentially very much like in linear algebra. You use induction. So first, since it is a separable space, you can pick at least one countable dense set. Let's do this here, and well, let's call the vector, say, z inside. Those vectors in general are not going to form your linearly independent spanning set, but we can easily convert this countable dense set to a linearly independent spanning set. So how to do this? Well, first we may assume that all the vectors in this set are non-zero. If some are 0, just throw them out. And then, well, you have to begin somewhere. So just pick the first one, call it y1. And now in an inductive fashion, if zk is linearly dependent on the previous k minus first vectors z1 up to zk minus 1, well, then you don't want to keep it, right? Because you want to construct something linearly independent, so you drop it, right? Remove it. Remove zk. Otherwise, well, keep it. Otherwise, keep it and relabel it, so let it be the next y. Okay, and this procedure inductively it works because you have only countably many vectors in your well, countable dense set, right? That's what it says from the get-go. Okay, so now we have to check that indeed this way we achieve those two properties, but that is easy because what we do is we discard linearly dependent vectors, so surely what we end up with is linearly independent. That's precisely how the construction works. So in this fashion we clearly satisfy condition 1. Moreover, throwing out only linearly dependent stuff, the set of all linear combinations of the yj's is exactly equal to the set of linear combinations of the resulting the set, I should read it the other way, the set of linear combinations of the zk is exactly equal to the set of the linear combinations of the yj, right? Because you create the yj's from the zk's by only throwing out linearly dependent zk's, but that doesn't affect the span, right? Okay, so that being said, and since what you start with is already dense, so z1, zn is dense in H, well then so is the span of those, right? If you have a dense subset and now you form linear combinations of those elements in your space, then, well, the result is the span is still going to be dense. That doesn't destroy density at all. It's dense in H. We also satisfy condition 2, and that's it. Okay, that's the end of the proof. So using induction in the way you construct things, this is super easy. Let's do an example. That is, I said, I think in the last video, that soon we will discuss, or we will show, that there's actually only 2 types of separable Hilbert spaces, and one of them is the one that I'm going to present now, so I should show that that guy really is separable, right? So it will be small L2, so consider small L2. Remember, these are as a space of sequences. Each vector in it is a sequence, and those are these square summable sequences. And that is a Hilbert space that we proved with the following inner product. Well, let's write it here. X, Y is n1 infinity, xn, yn bar, right? So xn is the nth entry of the sequence x, and likewise yn, the nth entry of the sequence y. Okay, that's a Hilbert space. Good. Now, claim is that is a separable Hilbert space. So here is a countable dense subset, which automatically will be a linearly independent spanning set. So that's how I choose it. I don't have to go back to the proof of the last result and do this operation of discarding, possibly linearly dependent elements. No, it will, from the get-go, it will be linearly independent spanning set. Okay. So here, how to do it? Well, it's very similar to what you do when you work in Rn, right? The canonical orthonormal basis in Rn are the Cartesian vectors, right? Those are those guys that have only one entry non-zero, and that entry is precisely 1, right? That's the simplest basis that you can think of. And here we will do the same thing, though now here I'm not in Rn, but in a sequence. So in a sequence space, that meaning, the entries go all the way up to infinity, but nevertheless the same idea. So here let's look at those elements, E and K. Those are all sequences. So we need the double index here, the K. And what is K? Yeah, well, exactly as in the Cartesian case. It is most of the time 0, precisely when K is different from n, and only once a 1 survives when K is equal to n. Okay, then the claim, then this set is a countable. That's clear, well, because the index runs through all the natural numbers, so it's clearly countable. It is independent precisely for the same reason why the Cartesian vectors are independent, right? If you sum them up and set them equal to the 0 vector, in this case this would be the sequence with all the terms equal to 0, then this is only possible if all the scalar coefficients in your sum are identically 0. Okay, so it's independent, and it is a spanning set. Spanning set for L2n. So maybe let's write this out. So if you have sequence x, maybe this time I write it like this, is in L2. Yeah, and of course, these elements, they should be in your space, they should be in L2. I didn't say this at all, but this should be clear, right? So this is a sequence of sequences where each term where only one term survives. So of course those sums are going to be finite. They're all going to be equal to 1, right? So maybe let's write this here. So En in 2 norm is precisely equal to 1 for all n, right? So that's clear. So that thing is certainly in L2. And now how do I represent each x of this type? Well, that's easy. Then x is equal to n from 1 infinity x n en, right? That is the linear combination expression for x, because here these guys, these are your scalar coefficients, and these guys, these are your vectors that form the linearly independent spanning set. And you can convince yourself, right? So careful here. This is a sequence, and so is this, right? The scalar coefficients here out front are here, the small xn's. Okay, and that precisely, when you look how the en's were defined, gives you that this is precisely equal to that. Okay, so this works nicely. Okay, then this, in summary, L2n is a separable Hilbert space. Okay. It will be one of the two prototypical types of separable Hilbert spaces to be discussed very soon. Okay, but before we do this, now the earlier theorem was about the existence of orthonormal bases, right? So we're not there yet. In the separable case, what we currently have is linearly independent spanning sets. So now the question is, how do you, or can you, turn those guys into orthonormal bases? And the answer is yes, and it's exactly done in the way that you do it in linear algebra. You use Gram-Schmidt orthogonalization algorithm. Okay, so this works here as well. And that's the formula that I'm going to present. It's proven exactly in the same way as in linear algebra. Okay, so let's write the statement. Gram-Schmidt procedure or algorithm that you can implement on a computer, say. So Yj be a countable, well, either finite or countably infinite, independent spanning set of a separable Hilbert space H, and that this set exists was the content of the previous proposition. Okay, now define xj inductively by same formula as in linear algebra. So you can make sense of this formula geometrically by looking at orthogonal projections on some orthogonal complement, but we haven't discussed projections yet, but we will in time. So I'm not going to use that language at the moment anymore. Just going to write down the formula. Everything has to be normalized. Yj xk xk. So what's in the denominator is just the norm of the numerator. Okay, you define them like this, then xj j1n is an orthonormal basis. Exactly the same statement as in linear algebra. The only difference here again being that this capital N in general is not finite, but could be infinity. Okay, that's the statement. Okay, so starting with a countable independent spanning set in a separable Hilbert space, then you cook up these new vectors xj, and then their collection is an orthonormal basis. That's the statement. Okay, so how to prove? Well, first, by condition 1 of the spanning set, in the previous proposition, we noticed that the vectors in the numerator of, let's say, yellow star, or the vector, yeah, I should say the vector in the numerator of star is non-zero. Why is this? Well, look, So the vector in the numerator in that norm is the same vector as in the yeah, okay, yeah, sure. The vector in the norm in the denominator is the same vector as in the numerator. So why is that one non-zero? Well, suppose this guy here on top were equal to 0, then this means that you can express the yj's in terms of the first j minus first xk, right? Yeah, but since this is an inductive formula, this means that you, because the xk then is expressed in terms of the first k minus first, say xl, so on and so forth, right? So if this were 0 here on top, that means that yj would be in the span of y1 up to yj minus 1. Yeah, but that's not going to happen because it's a linearly independent spanning set, right? That's precisely how we constructed it. We threw out all those linearly dependent things, okay? That's why the vector on top is non-zero, and that's why you can divide out its norm, okay? So this formula is indeed well defined here, the yellow star, okay? It's non-zero, so we may divide by its norm. Okay, now I said earlier the proof is exactly the same as in linear algebra. Well, by that I mean a direct computation. This is an inductive argument. You can look into your lecture notes in linear algebra. Verifies that the newly constructed vectors, they are indeed orthonormal. So that this set is an orthonormal set. And that proof is exactly the same as in linear algebra. You just perform induction, okay? You do the base case and then, you know, lift it to arbitrary, well, x sub j. So that I'm not gonna copy paste from the linear algebra lectures. It's exactly the same, okay? Instead, we will prove that that thing is indeed an orthonormal basis using our definition of orthonormal basis. Right, so an orthonormal set not properly contained in any other orthonormal set. Okay, so let's do this. So moreover, since star yields, so let's do some algebraic manipulation. What I'm going to do is up here, I'm going to move the denominator to the left, and then I'm going to solve for yj, okay? So what do I get is the following. So we have yj is equal to length yj minus k1 j minus 1 yj xk xk and then xj and then that remaining sum k1 j minus 1 yj xk xk. Maybe let's move it a little bit to the left like this. Okay, so what does this formula tell us? Since this we have for each n, well, if you now look at the set of linear combinations of the yj's, alpha j yj, say alpha j in your scalar field, either real or complex number field. Yeah, but here what this formula tells you is that the yj, this is a scalar, and here's a vector, and there's the vector, right? This is also a scalar. So that simply means that yj is a linear combination of the x1, x2, all the way up to xj vectors. So in turn, the set of all linear combinations of the yj's is equal to the set of all linear combinations of the xj's, right? Ej in F. Okay, this is also the same thing happens in linear algebra, that the span of the stuff that you newly create by Gram-Schmidt is exactly the span of what you start with. That's essentially what's written here, right? Okay, so we have this. And thus we have for each n, and thus remember the condition here for a linearly independent spanning set, namely those yj's, is that it's dense, right? The set of all linear combinations is dense in the Hilbert space. And that's what I'm going to use now. And thus the union over n of the right-hand side, meaning the linear combinations over those xj's, the right side sets, is dense in H. Okay, so in other words, what I just showed is that these xj's that you create from the yj's is also a linearly independent spanning set, right? Because orthonormal vectors are in particular linearly independent. Exactly proven as you do it in linear algebra. Okay, so now the only thing is that we have to show that it's an orthonormal basis. Okay, so that completeness we have to verify. Not completeness in the sense of Cauchy sequences, but completeness in the sense that you can't adjoin any other non-zero vector to it to create something larger than you already have. Okay, so let's do this. So to show the verify the completeness, which I discussed when I defined the orthonormal basis, I said this is an if and only if condition. You have to assume that a vector is orthogonal to all those xj's, and then you have to show that this can only happen when the vector itself is equal to 0. Okay, so let's do this. If, say, w is orthogonal to all those xj's, well, here's a neat way of writing this. This just means that it's in the orthogonal complement of those xj's, right? By definition of the orthogonal complement, this means that w is orthogonal to all those xj's, okay? Then w is also orthogonal to that aforementioned union of the right sets. But since that union is dense in H, and since the inner product is continuous, that means that also W is orthogonal to the whole space, right? Then W is orthogonal to that aforementioned union, and so to all of H, right? So in particular, it is orthogonal to itself, and then you're done. That means the inner product of W with itself is equal to 0, which is the norm, and this means that W is equal to 0, as you wanted it, right? As I said, we have to show that if W is orthogonal to all those xj's, this can only happen when W is the 0 vector, and that implies completeness of the orthonormal system or the orthonormal set, and hence the fact that it forms an orthonormal basis. Okay, let's write this down, then we will be done with this proof. This shows that the xj's, j from 1 to n, is a complete orthonormal system, aka orthonormal basis for H. Okay, that is that. All right. That's the theorem. So Gram-Schmidt works exactly in the same way, with the same outcome as you know it from linear algebra. Okay, so now there's one thing outstanding in this section, and this is what I mentioned now today and last time, that if you are in a separable Hilbert space, then more or less there's only, you know, two choices for that space. One choice will be the small L2 that we just discussed, and then the other choice, well, will be the coordinate space. So this is the last theorem that we will prove early on in the next video, and then we'll be done with the Hilbert space chapter, well, at least for now. Hilbert spaces, they will reappear, of course. These are the good spaces to work in. We will use them when we will discuss in more detail linear operators and spectral theory in chapter 4. In particular, the very big theorems towards the end of this module, they are formulated in Hilbert spaces. But nevertheless, I discussed Hilbert spaces early on because I thought these spaces share a lot of the geometrical features that you know from linear algebra. And if you go through the results, that's clear. Almost everything in some way generalizes something that you know from linear algebra. So it's a good starting point for infinite dimensional vector spaces. Okay, I will see you in the next video.